Kia ora and welcome to video 20 in the series Delightful Differentiation. Today's problem is a short little optimization question. We have a semicircle with radius 1 inscribed inside an isosceles triangle. The angle at the top is 2 theta. We could make it theta, but it makes it easier with the maths if it's 2 theta. What is the smallest and largest area that the triangle could have? So of course, if we change theta, the triangle will change its size. So good luck with the question, and we'll see you after the intro music for the solution. Okay, so this is a short and sweet question. We just need an expression for the area, and then we're optimizing it because we're finding the smallest and largest possible areas. So our area expression is going to be in terms of theta. Theta is the only variable in this problem, the only independent variable in this question. The key thing is to realize that this here is 1, and that's a right angled triangle. Well, it is if I draw the hypotenuse in. Okay, so that is a right angled triangle. We have an opposite side of 1 if that angle there is theta, and then we can work out the other sides of the triangle. Particularly what we need is the height of the triangle. We can work out that the height of the triangle there is cosec of theta, or 1 over sine of theta. Okay, and that's just by labeling the sides. That's the adjacent side of the right angled triangle. The opposite side is 1. We don't care about the adjacent side of the triangle. Opposite and hypotenuse means sine of theta. So we have sine of theta equals opposite over hypotenuse, and then rearranging that equation gives us the hypotenuse is 1 over sine. Okay, so that's the height of the triangle. We also need the base of the triangle. The base of the triangle is 2 times 1 over cosine of theta. So how do we get that? What you need to realize is that we're now heading over to this side, and we have another right angled triangle. The top angle is theta. The adjacent side of that is now 1 over sine of theta. This is now the adjacent side, and this is the opposite side. So we're using tan of theta. Tan of theta is equal to opposite O. I should never use O really as a variable choice. Over the adjacent side, which is 1 over sine of theta. Therefore, 1 over sine of theta multiplied by tan of theta is our opposite side. Tan is sine over cosine, and the sines cancel, so we get 1 over cosine. Okay, so that means that the base of our triangle is 2 over cosine, 1 over cosine in both directions. Alright, we've got enough to work out the area expression for the triangle. Area of the full triangle is half times the base, 2 over cosine, times the height, 1 over sine. The 2's cancel, and we're left with 1 over cos times sine. We could differentiate that expression. It's actually probably easier if we turn this into 2 over sine of 2 theta. It means that we don't need the product rule when we differentiate. We can just bring the sine of 2 theta up the top, sine of 2 theta all to the power of -1, and use the chain rule. So think about where I got this from. Cosine times sine is the same as a half of sine 2 theta, because sine of 2 theta is 2 sine theta cosine theta. Alrighty, we've got that. We've got all we need. We want dA d theta. We're trying to find the min and max of the area. In terms of theta, we differentiate this -2. Sorry, not in terms of theta. What was I talking about? We're finding the values of theta that give us the min and the max area. Sine of 2 theta to the power of -2 multiplied by the derivative of sine of 2 theta, which is 2 cos 2 theta. That equals 0. This factor here is not equal to 0 because it's in the denominator. It's sine of 2 theta all squared down the bottom. Therefore, it must be this factor that's generating the solution. So we can go cosine 2 theta equals 0. Cosine of pi over 2 is equal to 0. Think about what a cosine graph looks like. That's pi over 2. Therefore, 2 theta equals pi over 2. Theta must equal pi over 4, which is actually the only possibility because, or is it? Is it the only possibility? 45 degrees. So if this is 45 degrees and this is 45 degrees, what would that generate? That's a right angle triangle. Would that be the minimum or the maximum? Let's go back to the area expression. Let's think about this area expression without even doing differentiation. Right. Sine of 2 theta is bounded between 0 and 1. The sine graph is always between 0. No, it's not. It's between -1 and 1. But because the area is positive, sine of 2 theta can't be a negative number for this problem. So we've got that inequality there. And that tells us, if we think about what the sine graph looks like, if we want this to be positive, then we've got restrictions on the angle. 2 theta must be between 0 and 180 degrees. Okay, which means that our angle must be between 0 and 90. Okay, if we don't have theta between 0 and 90, then we're not going to get a triangle. I mean, if you think about the limitations of this setup, if we had a really, really wide angle at the top, we're going to have a massive area because the base is going to be tending towards infinity. And it is possible to have a really, really wide triangle at the top there. No, it's not, because it's not tangent to the circle. Not that one. The top will get really, really close to the circle, but will shoot off at a very wide angle. So, that area there is going to be tending towards infinity. I guess that's what we need to do and go back to our area expression. Does it tend towards infinity? So, this area expression, sine of 2 theta, the maximum that we'll get is 1. So the area is going to be smallest at 2 if we divide by 1. If we go 2 divided by 0, then we tend off to infinity. So, I was right. There is no finite maximum area. The area can tend off to infinity, so we don't actually have a maximum, but the minimum area is 2. And we get that down here when theta is equal to pi over 4. We substitute pi over 4 into the area expression, and we get 2 over sine of 2 times pi over 4, which is pi over 2, and that equals 2. That is a minimum area. I guess we could use derivative tests to prove it, but the logic also holds. But there is no maximum area, as we can make a tend to infinity as theta tends to 90 degrees, bearing in mind that the angle at the top was 2 theta, so theta tending to 90 is the same as saying this angle here is tending to 180. Alrighty, there is another way of solving this problem. I'll leave this as an exercise for you guys, but you may have actually done it this way, but you can show that the area of the triangle is cotan of theta plus tan of theta. And if you can show that, it's the same process. You differentiate, make it equal to 0. But it was quite nice having an expression for the area that's just a single fraction, because then we can reason with its min and max value. Have a good weekend.